So our final speaker for this session is Daniel Atwater, and he's going to be speaking to us about Antarctic Fast Ice Model CICE6 standalone forecasting. So take it away, Daniel.
I think I've unmuted myself here. Am I coming through?
Yes, that's correct, Daniel. Can hear you loud?
Great. Thanks for that, Jordan. Hey, I want to say first off that it's a real honor to be presenting to you today. It is something that I'm getting my motor started back up into science, so to speak, and I'm a part-time PhD student with the University of Tasmania, and I'll get into that a little bit more. But first, before I begin here, I would like to first acknowledge the deep history and culture of the traditional owners on the land on which I present to you this talk, as I'm coming to you from Hobart and the Muwininya people, past and present, and acknowledge their deep ties to this land and sea. So I first wanted to just say that up most importantly, but then offer up an apology for my intention was to be in Antarctica, providing you some real-time footage, so to speak, of the disintegration of the marginal ice zone and land fast ice as we transition into the summer season. But alas, I'm not doing that. I am a part-time PhD student, as I said previously, as I like to think of myself moonlighting as a METOC officer in the RAN, and currently seconded here to the Bureau of Meteorology to provide forecasting services to Antarctica for the summer ahead. And I say that because I think there's a lot of, well, I want to pay my gratitude to my supervisors because of their enduring patience, and I'm learning how much patience it requires to take on a part-time PhD student. And you can see I'm lingering here on this title slide, mainly because I was hoping to have a significant, or at least a little bit of results for you. But this is going to be mainly an aspirational talk about the next few years ahead. Probably more like 5 years. And Antarctica Fast Ice Model is something that is really coming and growing onto my heart in a nice way. It's like a butterfly. It's not a bad growth. But maybe talk to me in 5 years. So improving the coastal Antarctica sea ice ocean model realism as a method for more deeply understanding the dense shelf water formation. It's that last bit that is really going to be the science portion of my efforts. And I am trying to advance the slides then, and we have, it looks like maybe success on both my end and your end. And so this is not a suck eggs type of slide here for those members in the room, but it's really to showcase the different types of the vast amount of types of sea ice that we get, both in the marginal ice zone and then forming on the coast and becoming land fast ice. We've got grease ice and pancake ice, frazzle ice, nillas and shuga. We've got young ice and old ice. So sea ice is a mixture of all these different types, and I think the authors of the model that I'm going to talk to you a little bit more about CICE have put it in a logical framework that I think works really kind of good in that it is a distribution of thicknesses. And so really they've broken this up into a partial differential equation for ice thickness distribution. Obviously, it's made up of an advection term there against a thermodynamic term in the thickness regime. So how thick the ice is getting, that's that second term there to the right of the equal sign. And then we've got this ridging and redistribution function, which it is tantalizing to probably focus in on that when looking at, I think, the marginal ice zone. But I also think this lateral melt rate to the right. They're all very interesting terms, and I'd like to break those apart more. But first, I'm going to tell you a little bit more about why fast ice is the warrior ice, I'm calling it. And it was really good to see Rob's talk. I didn't collaborate with Rob beforehand to call it the last defender. I think I came to that conclusion independently, but that's probably because I've read a lot of Rob's papers and obviously others who have concluded, so not to the extent, not the hyperbole that I'm making it here of being the wear ice, but really it is attached to the coast, and it does buffer, buttress, and bond to the ice shelves that we are observing disintegrate into the Southern Ocean. And so this conceptual model that has been drafted up and is in preprint with our review of fast ice is showing the various components of what goes into fast ice in terms of the katabatic winds, obviously a major feature to the near coast environment, the oceanographic features of the circumpolar deep water being a flow into this area and providing a catalyst, if you will, for some dynamics that are going on with polynya formation, and the to the left, to the leeward side of fast ice, we typically get these polynyas. So I feel like these are some interesting components, but the important part is that we really don't fully understand circumpolarly the major mechanisms for fast ice formation and disintegration. So taking now a little bit more instead of the conceptual macro view, looking a little bit more at the micro view, but splitting fast ice up into the major components of rough and smooth. And those two are really how it's kind of describing how it's formed, whereas the rough ice is, you can imagine, as these jumbles of dynamic wind and wave events are pushing around this ice. We can imagine that these is getting very jumbled up, as in the top left image is trying to, or as it showcased there with some individuals, looks like going across the Arctic ice. And then down on the left is the McMurdo Sound, and that's the type of smooth ice that forms at a little bit slower of a pace when the thermodynamics, in both cases, the thermodynamics are at play here, but the slower ice is where we're getting that slower growth, but it's also between 50 centimeters and 2 meters, whereas the rough fast ice goes from 1 meter up to 10 meters, and that's because of that jumbling effect. So I also call fast ice a cozy ice, and I think that's just try to continue with this play on words that I'm going for here. But when we look at fast ice in the circumpolar aspect, this is a plot that Alex had produced, and I'm sure through his, if you get a chance to ask him about it, maybe the calluses on his fingers will tell you just the amount of work that probably went into making this. It was from 2000 to 2018. And so we're looking at fast ice concentration around Antarctica. And we can see here the various forms and patterns around Antarctica that fast ice seems to favor. And obviously there's a bathymetric linkage here with the grounded icebergs. And so there's going to be an extent from the continent in which it's going to be limited due to that contour that's thrown out of 400 meters as kind of a rough guide. But each October, the fast ice reaches its maximum extent around Antarctica at these various locations, and then by mid-March, it has disintegrated to its minimum. Another really awesome figure that was produced by Nihashi and Oshima in 2015 really plays to what the role for fast ice and polynyas are. And in that, in this slide, excuse me, what we're looking at here is the blue colors represent the fast ice concentration, and then the red colors represent the Paulina size. And this is over a data set from AMSR, so the Advanced Microwave Scanning Radiometer, which was run over the years of 2003 to 2011 until that that sensor on the that was the NASA's Aqua, or still is the NASA's Aqua satellite. That that sensor has gone kaput, and this data set is from that work, and it again it shows the strong linkage there with the leeward favoring of Paulina formation and Paulina, or sorry, and fast ice. Excuse me. They also, in this paper, computed that ice thickness with their data set, which is really a wonderful thing to have, as ice thickness data sets are pretty scant. And I'm going to move on now and talk about why Antarctica fast ice is not easy to do, excuse me. And this is now presenting two figures from recent papers from Van Acter in 2022 and then Hout in 2021. Hopefully I've pronounced that name correctly. And these were from regional models that were set up on East Antarctica. And the Hout paper showcased the Nemo Lim ocean sea ice coupled model that was from a 1/24th degree model. And they captured, or I should say they prescribed the B9B iceberg that Rob indicated previously had sheared off the tongue of the Mertz Glacier or ice shelf, excuse me. And this, I think that what we're ultimately the take-home message here from this is that there is some inclination that tensile strength seems to be very important, as well as grounded iceberg. So having the tensile strength correct in the models is very important, as well as getting an idea of where grounded icebergs are. Possibly just in a statistical distribution sense, but maybe in a real geographical location sense as well, may prove to be extremely important for getting fast ice right. And so tensile strength, what is it? It is the parameter for one of the internal stressors in the momentum equation. And the momentum equation, I believe, was first derived by Kuhn in 1974. And then what we're looking at is a modified form from Lemieux, Jean-Francois Lemieux, who came out about deriving this in 2016, and then had these partial differential equations that were implemented to give us an idea of what the tensile strength is for the ellipsis aspect ratio when we add in an E value and a KT value. And then they went through testing that out in the Arctic and came up with these results for the parameterization that works best in the Antarctic. And as we can see here, that the KT02 and the E value of 2.0 happen to work well in the Kara Sea. It worked well in other locations that they reported in, those two values did, and similar values were used for the modeling effort in both the Van Acter and the Hout papers. So my work has just begun, and I'm using the CICE6 model, and I'm just kind of wanted to say a little bit about why I wanted to use the CICE6 as opposed to SI3. And that's really just because the CICE6 can be run in a standalone mode, and it has some really easy to bite off pieces. Should I ever want to get inside and begin using or modifying the subroutines to fit my my own imagination for how they might be used. Whereas SI3, it is a beautiful machine built for the express purpose of using it with Nemo. There are people that have used it outside of Nemo, but it looked a little bit too daunting to do that. Not to mention the Cosima community, who I've glommed myself onto. They are propelling themselves forward and using an MOM6, CICE6 coupled environment that I will be using down the track. And that's hence it's kind of lead me up to this last slide. Very text heavy. I don't expect us to go through all of this as it's just a laundry list of what I'm looking at for the next 4 months while I am in Antarctica is step one, or at least chunking off a good portion of step one. And that's taking CICE6 and running it in a standalone mode with various forcings. And I'm in the process of I just finished this actually yesterday afternoon of regridding the ERA5 down to 1/10 of a degree. And about to run it through CICE6 in a vanilla type of flavor, but then begin to play around with the model a fair bit. And you can see a lot of these questions that I want to answer are rather pedestrian, but I think some of them will begin to feed into the MOM6 and CICE6 coupled environment that I will be using next year and building upon this work. And if I do have some time, I do have some weird bits that I would like to answer as well that possibly could have some scientific interest. But I'll leave it there. I'm sure you guys are starting to get hungry too, and so I'll let you go for the afternoon. But I really do thank you, and I think the host of this meeting for letting me talk. So cheers.
Thanks, Dan. Any questions? And start with your name, Luke.
Hi, Dan. It's Luke here. Can you just explain what you mean by can the CICE6 flow size distribution get a rough, fast ice?
Yeah, so what I mean there is that the flow size distribution function is, I believe, integral at, so it's a hypothesis that the flow size distribution is going to be important for getting sort of modeling rough fast ice, as opposed to level fast ice or smooth fast ice.
Okay, thank you.
Oh, Pat looks like he has a question.
Yeah, hi Dan, it's Pat Wongpan here. I have a question about the comparison between models that you will have in the future and the observation. I mean, from Alex's work, we can have the fast ice distribution, but when you model, you will get the ice thickness. So kind of what your long-term plan to compare the thickness you get from the model with the observation for fast ice? Thanks, Dan. Yeah.
Thanks, Pat. I hope that thickness observations will become slightly more present by 2024. That's probably a bit of a stretch, but well, listen, if we can generate some funding, that Warbot instrument looks like a really cool device to strap onto a vessel, and maybe I can convince some Navy folk to take a swing down by to marginalize them? Probably not. But I think the Nuenia would be a great place to put an instrument like that on, and it almost seems like it should come like fabricated to the vessel. I don't know if that answers your question, but yeah, I'm hungry for observations, and I think thickness is extremely important when considering fast ice.
What was that? That's a different question. That's all right. So are there any more questions for Dan? Yes.
Hi, Dan. It's Rob Massam here. Hi.
Hey, Rob.
Hi, Dan. How important is, I should rephrase it, how much is snow incorporated into the model? Variability in snow processes, etc. Or is it just treated like a slab in the model?
It is treated like a slab in the model.
Yep. I was, yeah. I was just wondering whether that's an area of improvement, given the importance of snow in the system.
If I can munch on that towards the end of my work, I would love to. Yeah.